And the first one is by Jainta Paul. We're going to hear about HyTWIN, hybrid program semantics for digital twin-based security interventions in industrial critical systems.
Good afternoon, everyone. I am Jainta Paul. I'm a PhD student at the University of Utah and a member of IOTrust lab there. I work in the intersection of formal methods and industrial control system security and also artificial intelligence. So today I am going to present our work HyTWIN, hybrid program semantics for digital twin-based security interventions in industrial control systems. Our lives actually depend a lot on industrial control systems, like the water treatment plants give us fresh water, and then nuclear reactors, power grid, they give us electricity, and also the factory automations, they are useful too in our lives. Often these plants become victim of cyber attacks. The most renowned of them is the Stuxnet malware that performed adversarial actions against a nuclear reactor in Natanz. And then there are power grid attacks, cyber attacks in Ukraine. And in the United States, there are a lot of, there have been known to be many water treatment plant attacks, and they all have like devastating physical consequences. So it is important to know how these adversarial actions are performed and how can we detect this kind of attacks, and not only detect but also mitigate the consequences that happens due to these attacks. To know how these attacks are executed or how can we detect this kind of attacks, we have to know the components of a industrial control system and how the components interact with each other. And there is no better way to explain the components of an industrial control system than the Purdue model. What the Purdue model provides is it provides a standard of, for which how the components of an industrial control system should interact with each other. For example, this is the Purdue model of an water treatment plant. So at the top, we have the administration laptop and the business server that interacts with the next level, that is the historian and the engineering server. And then there is the HMI, which is the human machine interface, and SCADA, which is the supervisory control and data acquisition system. They interact with the programmable logic controllers at the next level, and then they interact with the physical components like the valves, pumps, the transmission pipes, and other physical components. Typically, the programmable logic controllers are responsible for performing the physical tasks. Like in this water treatment plant, the programmable logic controller PLC1 is responsible for transferring the water from raw water tank to the dosing tank. And it does so with the help of the water level sensors, the valves, the pumps, and the other physical parts like the transmission pipes, etc. And the question is how the PLC performs this complex physical task. It does so with the help of scan cycle. So a PLC continuously scans for input from the sensors. Based on the sensor values, it changes its execution logic, and then based on that execution logic, it performs the physical task through actuators like the pumps or valves. So when the physical task is being executed, the values of the sensor changes, and again the PLC takes the new value and again it changes its logic and executes that with the actuator. And PLC does so continuously until the plant is shut down or the normal operation cycle has been completed. Now we'll see how an adversary can compromise some of these components here. For example, sometimes in the water treatment, for example, this water treatment plant, the HMI or any other components, if it were exposed in the internet, the adversary can penetrate into that and actually cause some malicious activities. So the adversary can perform penetrate into either the administration laptop or the HMI, and then from there it performs reconnaissance, which is learning about the layout of the system, and ultimately it gets to the programmable logic controller. So when it gets to the programmable logic controller, it can perform a vast number of malicious activities. Like it can shut down the plant, it can shut down the pump or the valve, it can spoof the sensor to a wrong value that is not what it's supposed to be, and it can actually in this case, for example, it has the capability to spoof the sensor and the valve. So the question becomes, how do we detect this kind of adversarial actions? And there has been many techniques for detecting this kind of attacks, but one approach that has gained a lot of attraction in recent years is the digital twin. So let us learn a little about the digital twin. A digital twin is the virtual replica of the physical twin, that is the physical system. It interacts with the physical components, and based on some initial values of the physical system, it predicts the next values. It monitors the values of the system, and based on that, it judges if there has been an adversarial action or not. For example, in this case, the digital twin monitor will interact with the physical water treatment plant and then decide if there has been a malicious attack or not. The problem with digital twin is it depends too much on the physical dependencies among the variables. And if the adversary is so intelligent that it spoofs the value in a way that the digital twin cannot detect it, then the physical safety properties will be violated. So let's see an example here. Let's consider that an adversary has spoofed the water level sensor X1, and also it manipulates the valve to remain open when it should not be. The goal of the adversary here is to cause overflow of the water. And you can see this timing diagram here. The red dotted line represents the spoof sensor value. The green line here represents the actual tank level, and the black line represents the value predicted by the digital twin. So as you can see, if the adversary spoofs the sensor here and keeps the valve open and spoofs in a way that the digital twin detector cannot detect it, by the time the digital twin detects it, it will be too late. See, so most of the digital twin will predict the attack here, but by the time it predicts, like this amount of time has been passed. So for this reason, we need a way to not only detect attacks, but also force mitigations. And even if some attacks may not be detected, how can we ensure that the safety properties will be maintained? So that is where our framework comes in. So we introduce HyTWIN. Let's take a look at the overview of our framework. We have a database of known attacks and verified mitigations. From these known attacks and verified mitigation, we have a digital twin monitor that monitors the physical system here. And based on those known attacks and verified mitigation, the digital twin tries to find an attack signature. So after the digital twin finds an attack signature, we try to calculate the mitigation horizon. The mitigation horizon tells us how long do we have before a safety is violated. And we calculate it anyway, be it an adversarial scenario or a normal operational cycle, we calculate it anyway. After we have the verified mitigation, and if we can detect an adversarial action, we force the verified mitigation into the system. For example, this is the same water treatment plant I was talking about earlier. Here we have an adversary that has manipulated the valve and the sensor. And in the database, we have stored the verified mitigation, that is draining the water by keeping the valve, the next valve V2 and the pump P2. So that is how we prevent an overflow, but we will see details later. And we have formally defined each of our components in the paper, but we will also give an overview later in the slides. A little clarification here. Someone might think that we may need a large number of concrete attack database, but that is not actually true. We will see later that one attack program, we defined attack program, one attack program can represent a large number of concrete attacks. And the mitigation, as soon as we detect the attacks, we will force the mitigation immediately. But if some attacks may not be detected, we will explain later how we can maintain safety in those scenarios. And for our framework to work, we need some assumptions. We assume that the digital twin cannot be compromised. Mitigation logic is verified and will work. The mitigation channel, it cannot be compromised. The adversary can compromise the sensors, actuators, even the PLCs, but it cannot alter all the components at once. And the adversary cannot alter the digital twin model or the mitigation channel. So visually representing in our framework, these are the trusted components, and these are the components that are vulnerable or can be compromised by the adversary. So with these assumptions in mind, we will see how we can model the safeties of an industrial control system. So this is the same water treatment tank that I was talking about, and it has a safety property in terms of the water level. The safety property is that the tank level, it cannot go beyond the upper threshold, and it cannot go lower than the lower threshold. It has to maintain this safety property. So across infinite amount of executions, let's say, how do we ensure the safety is here? There are two ways to think about that. For example, let's take a look at the diagram here. We can say that the flow rate is either 0 or a concrete number based on if the valve is open or closed. But the thing is, in industrial control system, due to physics-based uncertainty, the flow rate can be anything between 0 and 5. It can be any number, any continuous number. So let's say the flow rate is a non-deterministic number. And how do we now ensure the safeties? We model the industrial control system as a hybrid program, where the continuous actions are the physics-based actions, like let's say the water level changing from 0 to the upper level threshold, and the discrete actions are the control logic actions, like let's say toggling the valve or keeping the pump shut, etc. We say that for all states in psi, for all states alpha, psi holds true, and psi is the here the safety property. And this is our safety property in terms of the water level. And we say it will hold across all the states that is comprised of the physical dynamics, that is the plant, and the discrete actions, that is the control logic. Here we have shown what are the continuous dynamics and what are the discrete actions. And we say that these safety properties will hold across infinite amount of executions as long as we have a initial property that is true. And the initial property here is that initially we assume the system is in safe mode, and the flow rate, which is the tank level, is between this limit. So we can actually decompose these states into scan cycle normal form. This was a work done in HyPLC. Actually, the combination of control and plant has been decomposed in a way that looks like the scan cycle. But one thing HyPLC did not introduce is what will happen if we introduce an adversarial action here. Did not model the adversarial action. So let us see how the scan cycle looks like if we introduce an adversary here. For that, we define an attack program. An attack program is a hybrid program, AI, that models adversarial control of our sensors or actuators or other cyber physical components. For example, the same attack that I was talking about earlier, we define the attack program here as V1, 1 and X1, X tilde minus delta, which is, this is the spoof sensor value, the value that the adversary has injected into the sensor, and this is the real sensor value, and this is the valve. Now, define system under attack. That is, if we introduce this attack program, how will the system interact, or how will the system look like? Again, this is the scan cycle, the normal scan cycle without any adversarial actions. And if we introduce the same attack here, this is how it would look like. Now we have, the system has two choices, either the normal control or the attack program. In this way, we have modeled the uncertainty. We don't know when the adversarial action will happen, but we have modeled this anyway. Now we define, let's take a look at some of the attacks that cannot be detected by the traditional detectors. For that, we define the attack detector. The attack detector, an attack detector is a predicate that evaluates to true if the system appears safe, and false, it exhibits behavior inconsistent with the expected model. So simply put, an attack detector will detect an attack based on some logic. If it can match the logic, then it will raise the alarm. Otherwise, it will not raise an alarm. For example, this is the same attack that I was talking about. And let's say we have a detector and it detects the attack based on the spoofed sensor value and the predicted sensor value of the digital twin. And it will raise an alarm if the difference is greater than this detection threshold. But if the adversary is so intelligent that it manipulates, it spoofs the sensor value in a way that it remains less than the detection threshold, then the detector will uh, never be able to detect the attack. So we define stealthy attacks. An attack is stealthy if it does not violate the detector predicate, and eventually it will violate the safety properties of the system. So like the sensor attack that I was talking, this is a stealthy attack. It will evade detection of the traditional detector, and if any actions are not taken, then it will violate the safety properties of the system. We will see how our framework can maintain safety even if we miss detecting these kind of attacks. So this is central to our approach, the mitigation horizon. We will define the safety horizon and the mitigation horizon here before explaining how our framework can maintain safeties in this kind of scenarios. To define safety horizon, the definition is let alpha be a timed hybrid program, and if P be a safety property, the safety horizon is the maximum time during which executing alpha from the initial assumptions which guarantees P. Beyond P, no longer hold. And based on the safety horizon, we define the mitigation horizon, which is, let's say, a mitigation program. Let's say a mitigation strategy be MX, and we say that mitigation horizon is the latest time after executing alpha when applying M still restores the safety condition S. So this is central to our approach. This essentially tells us how long do we have before the safety property is violated without any intervention. So now take a look at the same example that I showed earlier. This is again the red dotted line represents the spoof sensor value. The black line represents the level predicted by the digital twin, and the green line here represents the actual tank level. So at this point here, we have the mitigation horizon as calculated, for example, as 17.5 seconds, and the policy threshold is 3 seconds. So policy threshold is something that should be set by the administrator if the mitigation horizon at some point becomes less than the policy threshold, then we will force mitigation into the system. So the next point, the mitigation horizon becomes 12.5 seconds. That is, this is how much time we have for mitigation, and the policy threshold is still 3 seconds constant time. The next point, it becomes 7.5 seconds, and then the next point becomes less than the policy threshold. So at this point, we force the mitigation into the system, and this is how we keep the system safe. In the paper, we have described more complex scenarios where the adversary can manipulate more components, and we have shown that formally verified mitigation logic works in many complex scenarios and keeps the system safe. So conclusion, we have introduced HyTWIN attack modeling, that is, we formalized attacks and mitigations as hybrid programs in differential dynamic logic. We compute time bounds for safe intervention under ongoing attacks. And we introduced synthesized monitors and certified mitigations for probably safe runtime response. In future, we want to model more scenarios. We want to integrate this framework with existing industrial control system engineering and simulation. And we want to generate attack monitors and mitigations from high-level specifications. So yeah, thank you.
Thank you very much. Do we have questions? I'd like to start with one, actually. If you can go back to the first slide where you showed the graph of the actual tank level and the digital twin predicted
Yes.
and